we're now ready to prove our big theorem that we needed to prove that the definition of a permutation being even or odd really worked. And you'll remember that the problem was, what if there was a permutation which could be written as a product of an even number of transpositions and in some other way as a product of an odd number of transpositions? We need to prove that that can't happen. In other words, we need to prove this theorem that says that no permutation is both odd and even. So I've called this the odd exclusive or even theorem, because exclusive or is a logical connective which has the property that P exclusive or Q is true if either P is true or Q is true, but not both. And that's the kind of result we're trying to prove here. No permutation is both odd and even. And to help us get started, we need a lemma. And the lemma is about what happens when you multiply certain permutations. I'm not going to give the full proof of this because this is on coursework 2 as an exercise for you, but I will just try and get started. So you'll remember that, what we need to do here, we're trying to prove two functions whose domain is the set 1, 2, 3 up to n and whose codomain is the set 1, 2, 3 up to n. We're trying to prove those functions are equal. So we just need to check they've got the same output for every possible input. And to help us do this, I'm going to give these cycles involved some names. So let's read what's going on. We have some distinct numbers a and b, and then some numbers x1 up to xk and y1 up to yl. And we're trying to prove that the product of the two cycle AB, which I'm going to call S, with this cycle here, so A x1 up to xk, B y1 up to yl, which I'm going to call T, is equal to the product of the cycle A and then x1 up to xk, which I'll call U, and B and then y1 up to yl, which I'll call V. And to prove this, what I need to prove is that for every integer x, I need to show that S of t of x Okay, so as I say, this is on coursework 2, so I'm not going to do the full thing, but I'm just going to show you how to do one possible case when you're proving this. So you're going to have to split up into different cases according to what x actually is. So let's just look at the case. What happens when x is equal to a, for example? So let's look at S of t of a. Okay, what is t of a then? T of a is equal to x1, as you can see from the definition of t. And remember, all of these numbers, a, b, x1, x2, x3 up to xk, and y1, y2, y3 up to yl, are distinct. They are all different. So x1 is not equal to a or b, and that means S of x1 is just x1 again. If we now look at what u composed with v does to a, well, again, the numbers a, b, x1, x2 up to xk, and y1 up to yl are assumed to be all different. So a is not equal to any of the numbers b or y1 or y2 or yl. That means that v of a is just going to be a again. And looking at the definition of u of a is x1. So in this case, S of t of a was equal to u of v of a. And to complete the proof of this identity, you have to check that in any other case, S composed with t and u composed with v also agree. So I'll leave that to you on the problem sheet, and I'm going to move on with the proof of our theorem about oddness and evenness. And to make the proof work, we have to think about the number of cycles which exist in a particular disjoint cycle decomposition for a permutation. And when we talk about the number of cycles in a disjoint cycle decomposition, we are going to count all of the one cycles in that disjoint cycle decomposition. So that, for example, if we're talking about S4, the identity would have a disjoint cycle decomposition, including all the one cycles. It would look like this. So there would be 4 cycles. And if instead we talked about 1, 2, 3, so the 3 cycle 1, 2, 3, if we wrote out the full disjoint cycle decomposition, it will be 1, 2, 3, and then 4. So this would have 2 cycles. So when we talk about the cycle count, or how many cycles a permutation has, then we are counting all of the cycles in its disjoint cycle decomposition, including any 1 cycles that happen to be there. We're now going to prove a result which talks about how does the number of cycles change when you multiply a permutation on the left by a transposition. What the lemma says is that when you multiply a permutation on the left by a transposition, the number of cycles either goes up by 1 or down by 1. But that's the only way it can change. It can only increase by 1 or decrease by 1. And the proof just uses the permutation multiplication identity we proved on the last slide. So let's look, we'll do half of the proof here. The other half is in the lecture notes for this section. So the proof is, so let's let S equals C1, C2 up to CR be a disjoint cycle decomposition for S. And remember that we are including all of the 1 cycles if there are any. So if there are any 1 cycles in that decomposition, they're included amongst C1, C2 up to CR. So that means every number between 1 and n appears in exactly 1 of those cycles. So we have a transposition T, which we're going to multiply into S. So let's call that transposition AB, like this. And then there are 2 possibilities. Right, as I've said, every number between 1 and n appears in exactly 1 of the cycles C1, C2 up to CR, because we've included all of the cycles, even the 1 cycles. So there are 2 possibilities then. Either A and B belong to the same CI, or they belong to different CIs. So what we're going to do here is just the first case. We're going to look at the case of what happens when A and B belong to the same cycle. Well, remember the result that I mentioned a few videos ago, which told you that disjoint cycles commute. Again, you'll prove this yourself on coursework 2. So C1, C2, CR can be reordered any way I like, and I still will then have a disjoint cycle decomposition for S. For example, C1 times C2 is equal to C2 times C1. So if I want, I could write S is equal to C2 times C1 times C3 times C4 up to CR. So in other words, we can move any cycle we like to the start of this disjoint cycle decomposition. So without loss of generality, so let's say without loss of generality, A and B belong to C1, because whichever cycle they do belong to, I can simply move that to the front of the disjoint cycle decomposition. So in that case, T times S will be equal to AB times C1, which is a cycle containing both A and B. So what does that look like? Well, again, I'm free to write a cycle starting at any place in that cycle I like. So I choose to write that cycle starting at A. So I know this cycle contains A and B. So it must have an A and a B and then a bunch of other stuff. So if we just give some names to the other stuff, let's call the numbers between the A and the B x1 up to xk. And let's call the numbers that come after the B y1 up to yl. And you can now see how this fits with the lemma that we proved on the previous slide. Because now, from that lemma, you know that what you've got is A and then the x's in a cycle, and then another cycle with B and then the y's, and then the rest of the stuff. And this is a disjoint cycle decomposition for TS, and you can see that it has R+1 cycles. So the other case in which A and B belong to different cycles CI can be done very similarly, in fact using exactly the same identity, and in that case the number of cycles decreases by 1. You end up with R-1 cycles. So in any case, when you multiply a permutation on the left by a transposition, the number of cycles either goes up by 1 or goes down by 1. We're finally ready to finish our proof. And I'm only going to do this proof in the case where n, the symmetric group to which all our permutations belong, is even. The odd case can be done very similarly, only you have to swap the words odd and even over a few times. So throughout this slide we will assume that n is even. We're only going to do the case n is even. You can find the whole thing written out in the online notes. So we have an even number n, and we have transpositions T1, T2, T3, and so on, belonging to Sn. And I want to think about the number of cycles in products of transpositions. I want to see what we can say about the number of cycles in a product of k transpositions for any k. And in fact, we can say whether that is odd or even using the result from the previous slide. Because if you think about the identity, so the identity permutation, that's equal to, if we write down its full disjoint cycle decomposition, we've got to put in all the 1 cycles. And of course, we're assuming n is even, so that is an even number of cycles. So the identity has an even number of cycles. Now, let's think of T1 as T1 times the identity. Then you're multiplying the identity on the left by a transposition. That means the number of cycles either goes up by 1 or goes down by 1. But if you increase or decrease an even number by 1, the result is an odd number. So T1 must have an odd number of cycles. In fact, it's kind of obvious it does, because T1 is equal to, in its full disjoint cycle decomposition, it might be something like 1, 2, and then 3, and so on, up to n, so there will be n-1 cycles. But of course, maybe T1 is something else, but in every case it would have n-1 cycles. Okay, next step, think about T1 times T2. You know that T2 has an odd number of cycles, so T1 times T2 either decreases that number or increases that number by 1. When you increase or decrease an odd number by 1, you get an even number. So T1 times T2 would have an even number of cycles. And when you work out T1 times T2 times T3, I hope I'm not labouring this point too much, you know that T2, T3 has an even number of cycles. So when you multiply on the left by a transposition, that number decreases or increases by 1, so it becomes odd. Summing up, the number of cycles in a product of k transpositions is odd if k is odd, and even if k is even. And let me just emphasize again, we are doing the case when n is even here. The opposite of this will be true if n was odd. Okay, the number of cycles of a product of an odd number of transpositions is odd, and the number of cycles in a product of even number of transpositions is even. So why is that what we need? Well, what it tells us is that if our permutation S has an even number of cycles, then you can only write it using a product of an even number of transpositions. And alternatively, if S had an odd number of cycles, you can only write it as a product of an odd number of transpositions, because a product of an even number of transpositions would have the wrong number of cycles. It would have an even number of cycles. It follows that there is no permutation which can be written both as a product of an odd number and as a product of an even number of transpositions. We're done, and we know that our definition of the sign of a permutation really does work.